Now we're going to talk about general curvilinear systems. Curvilinear systems have basis vectors that are orthonormal and that can be position dependent, as we have discussed for the case of cylindrical coordinate systems and spherical coordinate systems. There are other examples of curvilinear systems such as toroidal, hyperbolic, elliptical, etc. And in these coordinate systems, the coordinates we will show, the generalized coordinates we will show as q1, q2, and q3. So that is to say we have qi, where I can take values 1, 2, and 3. These are the coordinates that represents the position of a point in a curvilinear coordinate system. The corresponding basis vectors are, orthonormal basis vectors, are q1 hat, q2 hat, and q3 hat. So we have basis unit vectors qi hat, where I can take values 1, 2, and 3. And now if we're going to talk about Cartesian coordinates of this point, the Cartesian coordinates, the ith coordinate, Cartesian coordinate, is a function of q1, q2, and q3. So there is a transformation between the curvilinear coordinate system and the Cartesian coordinate system. And we also have a transformation from the Cartesian coordinates to curvilinear coordinates. So each qi value is a function of x1, x2, and x3, the Cartesian coordinates. Now, how do we find qi hat? Remember, we talked about this in spherical and cylindrical coordinates. So we change the value of the coordinate, generalized curvilinear coordinate, and we look at the variation in the position vector. So if we change the value of phi, for example, by a small amount, this will be the change in the position vector. So we're going to look at the change in the position vector del r, position vector del qi, and also this has to be a unit vector, so we have to divide it by its magnitude hi. So magnitude hi, that is the magnitude of the partial derivative of the position vector with respect to the curvilinear coordinate qi, is the scale factor hi. Okay. And now you can see that this is just for each unit vector, we have this relationship. There is no summation implied in this notation, so there is no summation. Okay. And now we can write the position vector in terms of Cartesian coordinates as xj, ej hat, where each xj is a function of the curvilinear coordinates q1, q2, q3. So this is our position vector. Now if I take a derivative of the position vector with respect to the curvilinear coordinate qi, that means I'm taking a derivative of the Cartesian coordinate xj, which is a function of q1, q2, and q3, with respect to qi, and this is in ej hat direction. And the magnitude of this scale factor hi, which is the magnitude of del r del qi, the variation of the position vector due to a change in the curvilinear coordinate qi, this magnitude is, now we have for here a summation is implied, so we have x1 e1 hat, x2 e2 hat, x3 e3 hat. So we have to take the derivative of each of them and then take the magnitude. So we will have del x1 del qi parentheses squared plus del x2 del qi parentheses squared plus del x3 del qi parentheses squared, and this would be inside the square root. So this is how we calculate the scale factor, for example, using the relationship between the Cartesian coordinates and the curvilinear coordinates. So we need to know the transformation between Cartesian coordinates and the generalized curvilinear coordinate system. Now, if we have a displacement, that displacement dr, infinitesimal displacement, is del r del qi dqi, which is, because del r del qi is the scale factor hi times qi hat, it's hi qi hat dqi, and this implies a summation. So del r del qi has been replaced by hi qi hat. So this is h1 q1 hat dq1 plus h2 q2 hat dq2 plus h3 q3 hat dq3. So again, we have the summation implied over this index I here because of these two terms. So we have del r del q1 dq1, etc. So this summation, and for each of them we substitute these values. Okay, and these scale factors that we have are a function of q1, q2, q3. The differential volume d tau is not necessarily a cube. So we will talk about this differential geometry in the next video. So we have to consider the fact that the scale factors themselves are position dependent. Okay, so we talked about general curvilinear systems, other examples, toroidal, hyperbolic, elliptical, etc., where we have orthonormal but position dependent basis vectors, and the generalized curvilinear coordinates are qi, basis vectors are qi hat, and the transformation between curvilinear coordinates and Cartesian coordinates are given by these equations. And the qi hat is basically the variation of the position vector with qi divided by its magnitude, which we call the scale factor. And there is no summation here. This is the qi hat that we are after. And the position vector in Cartesian coordinates is xj ej hat. So if I take a derivative of this with respect to the curvilinear coordinate qi, that means I'm taking a derivative of xj with respect to qi ej hat. And we have two indices here, so there is going to be a summation. So this is del x1 del q1 plus del x2 del q2 e2 hat plus del x3 del q3 e3 hat, and its magnitude is square root of del x1 del qi squared plus del x2 del qi squared plus del x3 del qi squared to calculate the scale factor hi. Now if we have a displacement, an infinitesimal displacement, it's the variation of a position vector with qi, del r del qi multiplied with dqi. So this would be calculated as, because del r del qi is scale factor times qi hat, and so h1 q1 hat dq1 plus h2 q2 hat dq2 plus h3 q3 hat dq3. All right, and these scale factors, hi, are also position dependent, so the differential volume d tau in our calculations will not be necessarily a cube.